My name is Ignacio Cuiral, and I'm going to be talking about dynamic occlusion handling for real-time object perception. The main motivation for this is shape control for industrial applications, in which proper feedback is a quite difficult task. This is why deformable sensing is an ongoing research in the robotics field. The goal is the proper perception of deformable objects for manipulation purposes. This means we're going to be working in highly dynamic environments where there are robots, there are parts of bodies like a hand or people passing by. It's a highly dynamic environment that needs to be handled. So the problem formulation is the following. I have an object, which is my target object. I have a real camera perceiving the scene, and then I can detect the occluding elements. These occluding elements, which are those elements that are between the camera and the object, I want to avoid them and estimate a new camera position that allows me to perceive the object properly, but also to avoid said occlusions. This estimated camera, I want it to be at a certain distance from the object as I'm performing tasks on it, so I also need a space around the object that allows me to perform these tasks. This sphere is defined by an R sphere, and within this sphere I will define two sets of rays that will help me solving this problem. The first set is the perception rays. These rays will tell me the positions in the sphere from which I can perceive the object more perpendicularly. The second set of rays is the occluding element rays, and they will tell me the positions on the sphere from which certain parts of the object become occluded. The first set of rays, if there were no occlusions, will be my proper camera position. As you can see here, they are computed by the mean of the angles in spherical coordinates of each one of these rays. This initial computation, by just using the occlusion-free position, can be used then to begin my iterative process, in which I will project the occlusion rays, this is the red rays here, on a tangent plane, tangent to the sphere, that contains my previously computed camera position. I can also define a vector in order to move the camera away from the red dots here, which are the occlusion rays projections. This vector is the sum of the vectors generated from these occlusion rays projected on the plane, and with a common ending, which is my current camera position. Therefore, if I analyze those projected occlusion rays that lie within a circle of R seed size, I can move away the camera from the occluding element and get a new position, which in this case is t sub I plus 1. And then this position, which was contained in this tangent plane, can be brought back to the sphere surface, so I can repeat the process until no occlusion points lie within an R-seed circle. So in order to summarize this iterative process a little bit, first I get my occlusion rays and project them on a tangent plane. Then I check if there are no points nearby my actual camera position inside an R-seed radius. If there are, I compute the purple vector, which is my moving away vector, and get my new camera plane position. And then I bring it back again to the sphere surface, which is my solutions space. This is repeated until, as I said, until there are no occluding points nearby. So the whole process can be visualized here in this simulation. You can already recognize some of the elements we've been mentioning, such as the initial estimated camera position, a target object, and an occluding object. This plane you're kind of visualizing here with these points is the plane corresponding to the last camera position, and it contains the points projected from the proper perception rays, and the red points, which are the occluding points, the result of projecting the occluding rays. You can also visualize all the iterations that allow me to escape from those red points, the initial position and the final position, which would be the solution, that T sub I plus 1 contained in the sphere. As you can see, the camera moves upwards, which is the logical move that allows us to avoid the overlapping between the yellow object and the blue object, yellow-orangish. So you can also see the reprojected images, and it clearly works, as in the left we see overlapping, and in the right we can perceive the object properly. This can also be seen in these results videos. You can see the target object, which is a film case, a Harry Potter film case. And you can see how I use my hand in different positions as a occluding element, and how all the iterative process is also visualized with those different camera positions that move away from the occlusions and would allow me to perceive that object properly, perpendicularly, but also avoiding occlusions. It also handles different scenarios. For instance, here we have a double occlusion coming from two sides, so the camera goes upwards in order to avoid those. So that's it, and thank you very much for your attention. If you have any doubts, feel free to ask me.